Welcome to Review Lecture 4.1. Upon successful completion of this material, you should be able to describe the differences between series and parallel circuits, calculate the equivalent capacitance of a series, parallel, and combination circuit. Parallel and series circuits. A circuit is a complete closed path for the passage of electrical charge. Charge must have a complete closed path to flow. An open circuit is one where the path has been broken, so the charge does not flow through the circuit. This is usually accomplished by opening a switch in the circuit or by just disconnecting something. Circuits come in three types: series, parallel, and combo circuits. Combo circuit is a combination of series and parallel. The terms describe how the charge moves through the conductors, that is, wires, and components that make up the circuit. When analyzing circuits, we usually find it advantageous to simplify the circuit by finding its equivalent replacement. An equivalent circuit is the simplest circuit that could functionally replace the original circuit. This, by the way, is a parallel circuit. Parallel circuits have multiple paths for the charge to flow. So there's more than one way for the charge from the battery to flow through this circuit. A series circuit, by definition, has only one path for the current to flow. That's the main difference between these two circuits. We will cover these individually. First, we're going to start with parallel circuits. I like to think of a parallel circuit as a ladder. See the rungs of the ladder? And the charge can flow any one of these rungs, and it flows through all of them. Okay, parallel circuits have more than one path for the flow of charge. The flow of charge splits at each junction where the conducting paths split or join. These are junctions. The flow splits among the branches depending upon the relative characteristics of the components in each branch. For capacitors, Q1 equals C1V, that's just Q equals CV. Q2, that's Q equals CV, Q2 equals C2V, and Q3 equals C3V. Now notice the potential across these is always the same. So potential from the battery equals V1 equals V2 equals V3 equals V. Why is the potential the same? Because this is one equipotential surface. All of this is one equipotential surface. This is another equipotential surface. The total flow of charge through the battery is the sum of the flows of charge in all of the branches. So Q total equals Q1 plus Q2 plus Q3. So Q total equals Q1 plus Q2 plus Q3. The voltage, which is the magnitude of potential difference across each branch or path, is the same as the voltage across the battery, because this is one equipotential surface and that is another equipotential surface. This one is connected to the positive terminal of the battery. So all of this is positive, whatever the battery voltage is. This is negative terminal of the battery. Okay, so V1 equals V2 equals V3 equals VB equals V. That equals the voltage across the battery terminals, where all of these are magnitudes. We're going to ignore signs. Capacitors add in parallel. So the equivalent capacitance of a group of capacitors in parallel is the sum of the capacitance in the branches. So C equivalent is C1 plus C2 plus C3. If they're all exactly the same, for N of them, all the same, C equivalent is N times Ci, where Ci is the capacitance of 1. So we want to turn this circuit into that one. So we want to find the equivalent circuit that could functionally replace this parallel circuit. So we know that Q1 equals C1V and Q2 equals C2V and Q3 equals C3V. The total charge on the parallel combination is Q equals Q1 plus Q2 plus Q3. So that equals the quantity C1 plus C2 plus C3 times V. C equivalent is then Q over V, and that is C1 plus C2 plus C3. So capacitors add in parallel. The C equivalent is the sum of all the individual capacitors. The C equivalent is equal to the single capacitor that could replace the parallel circuit and have the same total charge and potential. Capacitors add in parallel. Also, remember that charge adds in parallel and voltage is the same in parallel. So C equivalent is larger than the largest individual capacitance in the parallel circuit. For N equal value capacitors in parallel, C equivalent is just the number of them times 1. Here's a series circuit, and series circuit just has one path for the current to flow. That's the definition of a series circuit. All of the charge flows through every part of the circuit. So Q, which is the battery charge, equals Q1 equals Q2 equals Q3. Q equivalent is just C equivalent times V equivalent. Q1 is C1 V1, Q2 is C2 V2, etc. The total potential across the battery is the sum of the potentials across all the capacitors. VB equals V1 plus V2 plus V3 equals V. Now we're going to turn this series circuit into this one, so that we will find the equivalent capacitance that could replace all of these. So we end up with V1 equals Q over C1, V2 equals Q over C2, V3 equals Q over C3. The total potentials V due to the battery is V equals V1 plus V2 plus V3. And we can combine this. That would be Q times the quantity, 1 over C1 plus 1 over C2 plus 1 over C3. We then divide to find Q equivalent, we say Q over V. So that is 1 over this combination of 1 over C1 plus 1 over C2 plus 1 over C3. We can rewrite that as 1 over C equivalent is the sum of 1 over Cj, where Cj is the individual capacitances. So and this is a handy thing, for a pair of two capacitors, it's product over sum. So if we only have two capacitors in a series circuit, we can say C equivalent is C1, C2, that's the product divided by the sum of C1 plus C2, so product over sum. C equivalent is equal to the single capacitor that could replace the series capacitors with the same charge and the same total potential difference as the series capacitors. C equivalent is smaller than the smallest capacitor in the original circuit, so this is a good way to check it. Voltage is add in series, charges is the same in series. For n equal value capacitors in series, C equivalent is Ci over n. Now, a combination circuit is something that isn't either purely parallel or purely series. It is instead a combination of parallel bits and series bits. And sometimes the bits are called subcircuits. For that kind of circuit, you need to identify the parallel bits and the series bit and how they are connected together. The best way to show this is with an example. We're going to find the equivalent capacitance for this combination of capacitors that's put across a potential difference V. We're going to assume that C1 is 12 microfarads, C2 is 5.3 microfarads, and C3 is 4.5 microfarads. The potential difference applied across the input terminals of this circuit is 12.5 volts. What is the charge on C1? The strategy is to find familiar territory. We find parallel and series bits. Here's a parallel bit right here. How do I know it's parallel? There are two paths for the charge to flow. See this junction here? The charge can go that way or that way. This is in series with this bit. So this parallel bit, C1, C2, is in series with C3 because there's only one path here. Okay, so I repeated the knowns and unknowns. C1 equals 12 microfarads, C2 equals 5.3 microfarads, C3 equals 4.5 microfarads, and V equals 12.5 volts. And this shows all of those things in case you're curious. And this is all the things like Q1, V1, Q2, V2, Q3, V3. We need to know C equivalent and Q1. The parallel bit, V1 equals V2. C equivalent is the sum of all the individual C's for this parallel bit. So C12 is C1 plus C2. We name it C12 to indicate that it includes both 1 and 2. So if you want to do that mathematically, this would be 12.0 microfarads plus 5.30 microfarads, and that would end up to be 17.3 microfarads. So C12 is 17.3 microfarads. We name it C12 to indicate that it includes C1 and C2. This is not C12, it's C12. Now the series bit is C3, which is in series with a parallel bit up here. So for series capacitors, 1 over C equivalent is the sum of all the individual 1 over Cj's. And the charge is the same when you're in series. So Q12, which is this charge through here, equals Q3, which is charge across C3, and equals Q123, which is charge across the whole thing, and that would be equal to Q from the battery, assuming there's a battery connected to this. So 1 over C123, which will be the equivalent capacitance, C equivalent, is going to be 1 over C12 plus 1 over C3. That is the series part of this. And the parallel part can now be plugged into C12. So it's 1 over C1 plus C2 plus 1 over C3. Now we can plug some numbers in here. 1 over 12.0 microfarads plus 5.3 microfarads plus 1 over 4.5 microfarads. And that equals 0.280 inverse microfarads. Now you can remember it's 1 over this. This is where people make this mistake. Now, as you put units on things correctly, you're not likely to forget this final step. C123 is 1 over this, 1 over 0.280 inverse microfarads. So it ends up being 3.57 microfarads, which is C equivalent. So that's this capacitance to replace all of these. Now we're going to say that Q equals CV. We're looking at this equivalent circuit. So it's Q equals CV. V123 is V, or 12.5 volts. That's what's coming out of the battery. Q123 is C123 times V123. So 3.57 microfarads times 12.5 volts. So Q123 is 44.6 microcoulombs. Now we have to sort of go back and sort of spread the circuit back out again. So we got to investigate the bits. So series bit, Q12 equals Q3, because Q is the same in series. That equals Q123, or 44.6 microcoulombs. So V3 is Q3 over C3, so 44.6 microcoulombs divided by 4.50 microfarads. And the micros are going to cancel out. You're going to wind up with 9.92 volts. V12 is Q12 over C1 plus C2. 44.6 microcoulombs divided by the combination 12 plus 5.30 microfarads. The micros are going to cancel out. You're going to wind up with volts. So V12 is 2.58 volts. So that's the voltage across the parallel bit. So V1 equals V2 equals V12, and V1 equals 2.58 volts. Q equals CV, so Q1 equals C1 V1, so 12.0 microfarads times 2.58 volts. So Q1 is 31.0 microcoulombs. That's the charge on Q1. Okay, now if you notice something, here's a check here. If you add the V12 plus V3 has to equal 12.5 volts. So 2.58 volts plus 9.92 volts, if you check that, it does equal 12.5 volts. Here's another example. Capacitor 1 with C1 of 3.55 microfarads is charged to a potential difference V0 equals 6.30 volts using a 6.30 volt battery. The battery is then removed and the capacitor is connected to an uncharged capacitor 2 with C2 equals 8.95 microfarads. When switch S is closed, charge flows between the two capacitors. Find the charge on each capacitor when equilibrium is reached. Okay, so then we want to write down the knowns and unknowns. C1 is 3.55 microfarads, C2 is 8.95 microfarads, V0 is 6.30 volts. V1I is V0. So that's the initial potential across the original capacitor. V1F is going to be equal V2F. Why? Because they're going to be connected together until the charge starts flowing. So in other words, they reach equilibrium. We don't know Q0. We want to know Q1F and we want to know Q2F. The physics of this is capacitors. So the formula Q equals CV and Q0 equals Q1F plus 2QF. That just means that the original charge on the first capacitor winds up being the sum of the charges on the capacitors after they're connected and reached equilibrium. So the algebraic solution, Q0 equals C1 V0 and V1F equals V2F. So then we can say Q1F over C1 equals Q2F over C2. And that also equals Q0 minus Q1F over C2. So then we can do a little bit of algebra on this, and we see that Q1F times C2 equals Q0 minus Q1F times C1. And then we do some more algebra. Q1F equals C1 Q0 over C1 plus C2. And that equals C1 squared V0 over C1 plus C2. So Q2F equals Q0 minus Q1F. That's just changing this and turning it around. So Q2F equals C2 Q0 divided by the quantity C1 plus C2. That also equals C1 C2 V0 divided by the quantity C1 plus C2. Now we're going to split it off. I want to find Q1F. So that is going to be C1 squared over V0 divided by C1 plus C2. Now we can plug numbers in. Here's our C1, 3.55 microfarads. We're going to square that, times V0 of 6.30 volts, divided by the combination of 3.55 plus 8.95 microfarads. And if you do this carefully, this is times 10 to the minus 6 squared times 10 divided by 10 to the minus 6, it'll end up 10 to the minus 6. So it ends up Q1F equals 6.35 microcoulombs. Q2F is C1 C2 times V0 divided by C1 plus C2. This is 3.55 microfarads for C1 times 8.95 microfarads for C2 times 6.30 volts divided by the combination of 3.55 plus 8.95 microfarads. And if you do this, this ends up, this is times 10 to the minus 6 times 10 to the minus 6. That's 10 to the minus 12 divided by 10 to the minus 6. It becomes 10 to the minus 6. So Q2F is 16.0 microcoulombs. We can check that Q0 equals C1 V0. That is 3.55 microfarads times 6.30 volts. That equals 22.4 microcoulombs. And that has to equal Q1F plus Q2F, 6.35 plus 16.0 microcoulombs. And it does come out. So we probably did this correctly. Is energy lost during this process? Well, we're going to repeat the knowns and unknowns. And now we have two more that we know. We know that Q1F equals 6.35 microcoulombs and Q2F equals 16.0 microcoulombs. The formula is U equals Q squared over 2C, or 1/2 CV squared. So UI, this is the initial energy, is 1/2 C1 times V0 squared, or 1/2 times 3.55 times 10 to the minus 6 farads times 6.30 volts squared. That is 7.04 times 10 to the minus 4 joules. At the end, we have UF equals U1F plus U2F. So that's the energy across each of the capacitors after the equilibrium has been reached. That is 0.5 divided by C1 times Q1F squared plus 0.5 divided by C2 times Q2F squared. And we plug in our numbers. The 0.5 here is the C1 of 3.55 times 10 to the minus 6 farads. And Q1F is going to be 6.35 times 10 to the minus 6 farads. I'm going to square that. Similarly, here's the 0.5. Here's the C2 of 8.95 times 10 to the minus 6 farads. And Q2F squared of 16.0 times 10 to the minus 6 farads. It ends up being 2.00 times 10 to the minus 5 joules. And yet it is definitely less than the initial energy. In other words, it's lost more than 2/3 of what it had. So yes, energy is dissipated as heating in the wires and as electromagnetic radiation as the current flows through the wires. Here's another example. We have a slab of copper, thickness of B equals 2 millimeters, is thrust into a parallel plate capacitor. The area of the plates is 2.4 square centimeters, and the separation between the plates is 5 millimeters. The slab is parallel to the plates and equal in area to the plates. What is the capacitance before and after the slab is inserted? If a charge of 3.4 microcoulombs is maintained on the plates, what is the ratio of electrical potential energy before to that after the slab is inserted? How much work is done on the slab as it's inserted? Is the slab sucked in or must it be pushed in? Okay, so the knowns and unknowns. We know that B, we converted everything to SI. So B, which is this thickness of the slab, that's the copper slab, is 0.002 meters. D, which is the plate separation, is 0.005 meters. The area of this, or the plates, is 2.4 times 10 to the minus 4 square meters. Q, which is the charge, is 3.4 times 10 to the minus 6 coulombs. Kappa is 1 for air. We need to know UI over UF and work. The physics of this is capacitors. The formula is C equals kappa epsilon naught A over D. U equals QI squared over 2C. Work equals UF minus UI. So the part A is what is the capacitance before and after the slab is inserted. So CI, which is without the slab, is kappa epsilon naught A over D. So 1 times the epsilon naught times the area of 2.4 times 10 to the minus 4th square meters divided by 5 times 10 to the minus 3rd meters, and that's the D. That ends up being 0.428 picofarads. After the conducting slab is inserted, the capacitor is now effectively 2 capacitors in series. Let the separation between the surface of the slab and one of the plates be X. Then the separation between the other surface of the slab and the other plate is now D minus X minus B. So it's like 2 capacitors. One with plate separation of X, and this slab is now both this plate, the wire connecting the 2 capacitors that are in series, and this plate of this other capacitor. This one, of course, has the plate of area A and a plate separation of D minus X minus B. CF is going to be C1F times C2F divided by the quantity C1F plus C2F. They're in series. That's where this comes from, product divided by sum. C1F is epsilon naught A divided by X. C2F is epsilon naught A divided by the quantity D minus X minus B. So we can substitute in here. CF is going to be equal to the quantity epsilon A divided by X times epsilon A divided by the quantity D minus X minus B divided by the quantity epsilon A divided by X plus epsilon A divided by D minus X minus B. If you get rid of all the terms that are common to this and cancel them all out, you wind up with CF equals epsilon naught A divided by D minus B. So it really does not matter where the slab is inserted, as long as it's between the plates, parallel to them, and of equal area of the plates. This is equivalent to a single capacitor which has had its effective plate separation reduced to D minus B. CF is then the epsilon naught times the area, which is 2.4 times 10 to the minus 4th square meters, divided by the new plate separation, which is 3 times 10 to the minus 3 meters. And that is 0.708 picofarads. That is a 66.7% increase in capacitance, which makes sense because when you push the plates together, the capacitance increases. Now, if a charge of Q equals 3.4 microcoulombs is maintained on the plates, what is the ratio of electrical potential energy before to that of after the slab is inserted? And is the slab sucked in or must it be pushed in? So UI over UF is QI squared divided by 2CI divided by QF squared divided by 2CF. And everything else cancels out. The QI and QF are the same. And then it becomes CF over CI. Why are the QI and QF the same? Because it's isolated. There's no place for the charge to go. So then this is equal to D divided by the quantity D minus B. So 5 centimeters divided by 3 centimeters, or 1.67. So UF over UI is 1 over 1.67, or a 40% decrease in energy, which means that the slab will tend to be sucked in. How much work is done on the slab as it's inserted? W equals UF minus UI, or 0.5 times the quantity QF squared over CF minus QI squared over CI. And at this point, we can say that is 0.5 Q squared times CF to the minus 1 plus CI to the minus 1, or 0.5 Q squared times the quantity D minus B minus D divided by epsilon naught times A. And that equals minus 0.5 Q squared times B divided by epsilon naught A. And it equals minus 0.5 times the Q squared, that's 3.4 times 10 to the minus 6 coulombs, that's squared, times B, which is the plate separation, 2 times 10 to the minus 3 meters, units conversion, divided by epsilon naught times the area, which is 2.4 times 10 to the minus 4 square meters. It ends up being negative 5.44 joules. Although copper is not a magnetic material, it will be sucked in. It is also not necessary that the slab be a conductor. A dielectric would also be sucked in. A circuit which has multiple paths for the charge to flow is what kind of circuit? If it's got multiple paths, it's either a parallel circuit or a combination circuit. Because a combination circuit would have multiple paths. It would include parallel bits as well as series bits. A group of capacitors is wired in such a way that they all have the same potential difference across them. These capacitors do not have the same capacitance. How are they wired? They're wired in parallel. You need to create a circuit with an equivalent capacitance of 10 microfarads, and all you have is 40 microfarad capacitors. What, if anything, could you do? Well, you want to put them in series because you want the equivalent capacitance to be less. So in this case, you want to wire 4 of the 40 microfarad capacitors in series. You need less equivalent capacitance than the value of the capacitors you have. You need a series circuit. If you wire 4 in series, series equivalence is CI over N, or 40 microfarads divided by 4, or 10. You have some 10 microfarad capacitors, and you need to create a circuit with a capacitance of 50 microfarads. What, if anything, could you do? Well, you need the capacitance, the equivalent capacitance, to be greater than any of the other ones. So you're going to put them in parallel. So you would wire 5 of the 10 microfarad capacitors in parallel capacitors and in parallel. You need an equivalent capacitance is 5 times the value of the capacitors that you have. You wire 5 in parallel. C equivalent is going to be N times CI, or 5 times 10 microfarads, or 50 microfarads. Thank you.